Right, yeah, so I'll be talking about harvesting the wisdom of crowds and several experiments that we've done. So I wanted to open this talk with a few well-known examples, I think they're well-known from the industry. So how many of you have heard of Rob McEwen from Goldcorp? No? I guess not that famous. So Goldcorp is a Canadian mining company that was about to go bankrupt in the early 2000s. And essentially, they had no mining fields. What Rob McEwen did, their CEO, is he put online all their geographical information, all their maps, all the information that they had stored in their computers, and he promised $500,000 of reward for anyone that finds a nice gold patch. So a lot of groups have worked on this problem. Essentially, he got the results. One group got the prize of $500,000. Whereas they had found roughly $3 billion worth of gold in various patches. So that's a huge success story in terms of crowdsourcing and relying on the wisdom of crowds. Another interesting work along these lines is the Netflix challenge. How many of you have heard of Netflix? All right, that's better. Getting worried there for a second. So Netflix is a video company. They gave $1 million of reward for people that were to improve their recommender system. They got a lot of different solutions, different algorithms, huge improvements with a huge business impact on their revenues. So again, another great success story. To show you that this is not always the case, I brought up the BP oil spill example. So you probably remember the famous story where BP has spilled a huge amount of oil on water. One of the things that they've tried to rectify the situation, they've tried a lot of things to no avail for quite a while, was to crowdsource the solution. So what they said is, if anyone wants to give us a solution to the BP oil spill, please come up to our online website, give us your solution. What can we do about this terrible oil spill? So a lot of people said, you know, this is just a press issue. They're just trying to avoid bad publicity, which they had plenty at the time, by trying to rely on other people. But be that as it may, they got roughly 100,000 different proposals of how to rectify the situation. So they had a big pile of experts going through these ideas, trying to sift out the best things that they could do. But again, there was nothing good. So they had a lot of solutions. Most of them were pretty much useless, or stuff they already knew that were rather simple. So there's a good question of what makes the difference between this example and the previous examples that were hugely successful. There are a lot of businesses that rely on the wisdom of the crowd. I guess one of the most famous is Wikipedia, where a lot of people aggregate their knowledge in one place, and that generates a huge resource that is very, very popular. There are a lot of other businesses that rely on similar things, starting from Linux, which is an operating system that was built on this principle of using the wisdom of crowds. Other companies like WikiTravel, which is a Wikipedia for travel resources. Things like Yahoo Answers and Mahalo, which are question answering services, and so on. There's a huge list. So obviously the wisdom of a crowd is a big thing, but you have to know what you're doing in order to harvest this wisdom. So even within Microsoft, we're using crowdsourcing in order to improve our search engine. What we're doing is we're aggregating human relevance judgments. So whenever there's a new change introduced to our search engine, Bing, we rely on several people, a lot of people, that go through the search results for various queries and try and determine whether the situation has improved or has actually become worse. So even within Microsoft, we're already using this kind of a technology. But the question is, how can we do this better? So there was a huge move from the world of outsourcing to crowdsourcing. When you're outsourcing a project, you're relying on one specific group that you've decided to use for your project. You know who is going to provide you with a solution, as opposed to a crowdsourcing setting where you have this blob of individuals. You don't know who is going to answer your questions, how they're going to do it, how they're going to solve your project. So there is a clear-cut line between these two worlds. So you can ask, okay, is this IQ of the crowd or the wisdom of the crowd, is this really a good idea? Can you actually use a crowd to improve the quality of your results? So as opposed to what happened in the BP example, where you have a huge quantity of results, but all of them are of lousy quality, can you actually improve quality by using these themes? You can also ask, okay, how many opinions do we have to aggregate? Is it enough to aggregate 10 people's opinion, 100, 1,000? maybe 1 million is where it starts to hit off. You can ask, how should you perform this aggregation? How do you melt all these opinions and ideas that people have into one giant brain? You can ask, how do you determine the best workers that are out there that you should use for these crowdsourcing tanks? You can ask how these people should be compensated in order for you to get good results. You can even ask, is the crowd actually more intelligent than just its most intelligent member, for example? Maybe it's just better to rely on one person's opinion as opposed to a crowd of 1,000, but pick this person well. So we've devised a wisdom of the crowd experiment to try and shed some light on these questions. Obviously, we will not be able to solve all these questions. These are high-level questions. But maybe shed some lights on this phenomena of the wisdom of the crowd. So our first experiment uses IQ questionnaires. So IQ questionnaires are a pretty standard way since the 1930s to measure people's aptitude, intellectual aptitude. One of the most commonly used tests is something called Raven's standard progressive matrices. It's fairly old, almost 100 years old now. It's fairly simple the way it works. You don't need very, very specific instructions. You just have a matrix like this one here, where you have 9 shapes, and you have to choose the correct answer to fill in this missing shape there. So it's been used in a lot of settings, including high stakes, like trying to find out the best military personnel, job screening, and so on. So we've used a data set of these questionnaires answered by people during the British standardization effort from the University of Cambridge's Psychometrics Center. And we have aggregated the responses. So just to tell you a little bit about the test and how the result looks like, there are 5 sets of questions. Each set has 12 questions in it. In all of them, you have one of these matrices, and you have to fill in the missing shape. So in total, you can have as many as 60 correct answers in total. In each of these, only one answer is actually correct. You can take a look and see if you can solve this one for now. In terms of translating it to the standardly known IQ scores, so usually during these standardization efforts, what you're trying to do is have a mean IQ of 100 with a standard deviation of 15. So there's a table mapping the number of correct responses that you got in the test to the IQ scores. So these are the actual results from our data set of roughly 1,000 participants in total. So as you can see, this is roughly a Gaussian shape with this area here about the mean. So between 35 and 38 correct answers would be your mean. And the IQ table is fairly similar. So one way to aggregate responses, that is a very, very straightforward way, is simply by using voting or majority voting. So the way this works, if these are your people, and these are the answers they have provided for each and every one of the questions, what you select as the crowd's response to each of these questions is simply the answer chosen by the majority of the participants. So in this example, almost everybody answered A, you choose A. In this example, most people answered D, you choose D, and so on. So that's a very, very simple way of aggregating the responses simply by majority voting. Maybe not the best way or the optimal way, but certainly a reasonable way. So this is our first experiment that we have done. What we had is, out of the entire population that we had of participants, we have sampled many, many crowds, just sets of people of a given size. So a crowd of 20 people, we've sampled many, many crowds of 20 people out of our entire population, and we've aggregated their responses using the majority vote. So what you see on the y-axis here is the IQ of the aggregated questionnaire. So again, I take, say, 20 questionnaires of different people. I choose the majority response for every question. That's my answer, my crowd's answer for that specific question. I score it just the same way I would score any standard human participant, and I get the crowd's IQ score, which is shown on this red line here. We've also tried a slightly different method of aggregation based on a machine learning approach, which I'm going to describe soon. But first of all, a few things about this plot. So as you can see, the IQ increases when I increase the size of the crowd, but the returns are rapidly diminishing. So there's a huge boost in crowd IQ if I add a few participants, the first few participants that I add, up to, say, a crowd size of 10 or 20 individuals. But beyond that, it's quite hard to improve the score. So this line quickly saturates. It's still going up, but very, very slightly up. On the other hand, very, very quickly, even with only 10 participants, I improved the IQ by 1 standard deviation. So it's like taking one individual 1 standard deviation above the population mean simply by aggregating the opinions of just 10 people. So it's a huge boost in performance if you use this as your measure. So indeed, there is something to this notion of the wisdom of the crowd. So it might be due to the sampling. As you can see, there is some noise. And the reason is there are lots of crowds of size, say 70, out of our entire population. We don't just plot the average across all of these because this is not tractable. All we can do is actually sample many of these. So I think we've sampled roughly 1,000 or 10,000 crowds, which gives you some noise. So I'm not sure if this is just a result of the noise or at some point there is some extra boost because of adding population. A few things about our machine learning approach. So there is a very, very easy way to describe how the data was generated, which lies at the heart of our machine learning approach. So this is a probabilistic generative model for the data. Essentially what it says is every question, Q, has one correct response out of all the possible answers. A priori, we don't know which one of these is correct. We have no reason to prefer one answer over the others. Every participant has an ability. You can call it an IQ level. You can call it just aptitude. Or you can just treat it as a probability of knowing the correct answer to any given question. So whenever we pose a question, if you have a high aptitude, high IQ, you have a higher probability of answering that question than someone that has a low IQ. The response of an individual to a question is if they know the correct answers, then they choose that answer. If they don't know the correct answer, then just choose a response at random, uniformly at random out of all the responses. So that's a very, very simple model that roughly explains how this data was generated. And what you can do is you can use machine learning techniques to try and figure out the aptitude of the individuals. Yes, Milan?
So the IQ is input. Where do you get that? For a general case, how would you get that?
Yeah, so what lies at the heart of probabilistic graphical models is exactly this idea that you describe a generative process, how this data was generated, but you don't have the specific parameters that were used to generate this data. In this case, the ability levels of the participants, their IQ, and use machine learning techniques to reverse engineer this. So that's what probabilistic graphical models are really all about. So using the machine learning lingo, this is exactly what we do. We use a probabilistic graphical model that describes this data. This is this model here. It says exactly what I've said before. For every question, there is one correct response. We have a uniform prior assumption about which is the correct response. We have an aptitude. That's our parameter that we're trying to figure out based on the data, which is the probability of an individual I of correctly responding to any one of these questions. With probability GI, then they choose the correct answer, and with probability 1 minus GI, they guess at random. So this thing here is called a factor graph. It describes our system, and then you use one of the many different possible machine learning approaches to reverse engineer these parameters. So we've used a method called expectation propagation, but there are lots of other methods that do similar things. Another question you can ask is a crowd really smarter than its individual members? And this is one way of making this question a bit more precise and actually answering it using the data. You can sample. So suppose we take the entire population, and we randomly sample a crowd of, say, 60 participants. We have two numbers for this sample crowd. One is the maximal IQ score of all the individuals within that crowd. If we know the correct answers, we can compute that. We compute the IQ levels of each and every one of the participants of the crowd based on their responses. And we also have the IQ of the entire crowd based on our notion of aggregation. So again, we can sample many, many crowds of any specific size. And we can plot the mean IQ of these crowds or the mean maximal IQ scores within that crowd. How intelligent was the most intelligent member in that crowd? So this is what's shown in this plot here for the entire population. So as you can see, this green line is the highest scoring individual within that crowd. For a crowd of 140 participants, for example, this is 135. So a really, really high level of IQ, the maximal participant on average for a crowd of this size sampled. So as you can see here, the most intelligent individual for this general population actually beats the aggregated wisdom of the crowd. So in this case, you would rather figure out who your smartest member is and only use their opinions as opposed to aggregating everybody's opinions. But that's not always the case. So suppose we focus on a slightly more homogeneous crowd. So suppose we restrict our population to only the people who have roughly mean IQ. So people with an IQ in the range of between 95 and 105. Now, obviously, if we sample individuals from this kind of a crowd, the maximal IQ of these individuals, if any of these members of that crowd, will never exceed 105 because that's how we chose this population. So that's what happens here. You see that this line quickly converges to 105. If you sample enough individuals from this range, you will hit one that has an IQ of 105. But when you aggregate the opinions of many average Joes like this, you have a much higher IQ score. So again, 1 standard deviation above the population mean. So these are average Joes. Their IQs are always not too high or too low. And yet, if you aggregate all their opinions, you get a huge boost in performance. So again, for a very, very homogeneous crowd, it's better to aggregate everybody's opinions. And for a very heterogeneous crowd, you would rather select the most intelligent individual within that crowd. So again, we tried this for various ranges. We also tried it, for example, for a high range of IQ, so people between 110 and 120. So smart people, very, very smart people. And still, it is better to aggregate their opinions as opposed to choosing just the best individual within that crowd. And the same holds for low IQ individuals and so on. Another question that we've looked at is, yeah.
One slide, right?
Yep.
So what's going on in figure 9?
Yeah. So in this line, we chose a slightly wider range of IQ scores. So again, people between 1 standard deviation below the mean, so between 85 and 1 standard deviation above the mean, 115. So average Joes, but with a bit more variance. And in this case, you can see that the crowd IQ tends to get closer to the maximal IQ, but the maximal IQ within that crowd is still slightly better. So this crowd is very heterogeneous. This crowd is slightly more homogeneous, but not very homogeneous. And this crowd is very, very homogeneous. In all of them, you have roughly the same mean IQ score. These are average Joes in these cases. But still, what matters is the variance in the population scores.
Do you have an explanation for why the aggregated score decreases at the end? I mean,
so yeah, it does seem like there are some questions that only people who have very, very high IQ levels can answer. And there is something called the distractor. So an answer that seems right to many, many people, but is actually not the right answer. And unless you can figure out that this is what's happening, then you have a question where a lot of people would answer incorrectly. And the more people you have, the higher is your probability to get that item wrong. So in this case, what happens is our model is not completely exact, right? We said that if you don't know the correct answer, you choose an answer uniformly at random. And in this case, what I'm saying is there's a question where there is a distractor, something that looks right, but actually isn't.
Do you have a test for that this effect is causing this decline at the end, or is this one?
We have some supporting evidence. I wouldn't say a concrete proof. I'll talk about this in a minute. So, yeah.
So I was wondering, so here you're measuring the IQ, but it's true that in those tests, basically, if you experience once, you are more likely to get higher scores.
Yes, so that's a general criticism of IQ tests.
One way to interpret this is that you are selecting the experience that people have in this specific context.
No, so that's incorrect. So what we do is, in retrospect, so what we do is we have a bunch of people, we let them solve the test, they solve it only once. So we have their responses only once.
So you ask them precisely whether they've been exposed to this type of problem.
No, so some of them may have been exposed and some of them may not have been exposed in the past. But still what matters is how you aggregate the responses. So you can train people up to a point in answering these IQ questionnaires, again, up to a certain point. But that still doesn't explain why by aggregating the information, you improve the performance, because the aggregation process is done later. They're not given a chance to solve the same test again.
And then you control also, so you aggregate just by the clarification question. You aggregate by answers.
Yes, we only look at the answers that they provided once, and we aggregate, exactly.
If I just have one right answer and all the rest is wrong, I'm going to reduce the performance on all the other answers.
On all the other questions, yes, you're likely to reduce the performance, exactly, for a crowd to which you're sampled, exactly. So the next question that we ask is, can we actually assign individual credit? So suppose I have a crowd IQ, I've got a crowd of, say, 100 people. I aggregated their responses. The crowd's IQ is, say, 115. So now I want to know which of the crowd members actually helped me a lot. Now, generally, you can say, well, maybe you should assign more credit to the people that have higher IQ scores. They're likely to have more correct responses, so they've helped the crowd more. But actually, if you think about it, that could actually depend on the context of a crowd. So suppose I have a test that's composed half of questions in English and half of questions in math. Right? And I've got an individual that is exceptional in math. And I add this guy to a crowd of people that have good English skills. He's likely to help them quite a lot because they would not do as well on his specific field. Whereas if I take a crowd of a lot of individuals, they're all experts in English, and I add another guy that knows English well, he's not likely to help them that much because he's not providing extra insight to something that is out of their area. So one way to look at it is using cooperative game theory. So in a cooperative game, what you have is essentially a characteristic function or a table mapping any team, any subsets of the people to their performance. In this case, the performance is the crowd's IQ. So using this experiment, this method of aggregation, I can take any subset of the people that I want, and I've got their performance measure, which is their crowd IQ score. Now, one of the earlier works by the famous Lloyd Shapley in game theory tries and assign individual credit or individual money in this case in settings like these. So this is the famous Shapley value. Essentially, what he tried to do is model power in weighted voting situations or to achieve fairness of a division of credit. The Shapley value is essentially the mean contribution that you have across all possible agent permutations. So this is this formula here. I guess a lot of you are already very familiar with it. Essentially, all it does is it runs across all possible permutations of the agents. In each permutation, you measure the difference between, in this case, the crowd IQ of the people up until our specific agent and up until our specific agents and including that specific agent. So essentially, how much would you add to a randomly selected team? How many IQ points would you add to a randomly selected team? The nice thing about this Shapley value in this case is that it would sum up to the grand total IQ score. So really what it does is you take this entire setting, you take the responses, and you can assign how many IQ points each individual is in charge of according to this notion of fairness. So here are the results. What you have on the x-axis here is the IQ score. Each dot is an individual. The x location is the IQ score of that individual. And the y-axis is what we call contextual IQ. This is just the Shapley value, or their contribution in IQ points towards the entire population. So again, this doesn't depend just on the individual and their IQ level, but also how much they contributed to that specific crowd, our entire population. So not surprisingly, the higher your IQ score is, the higher your contribution score is. So obviously, the IQ scores in this range are roughly 100 to 115. These are IQ scores. What you have here are contextual IQ scores. These are much lower numbers because all of these together have to sum up to the total IQ of the crowd. So these numbers are around 1 IQ points or half an IQ point. So within a crowd of 100 individual, I can say this guy is in charge of, say, 5 IQ points. This guy really helped a lot. So you can see that, of course, the higher your IQ score is, the higher you're likely to be in terms of your contextual IQ. But there is a wide variance. So even if we consider just individuals that are here have a mean IQ score, so not very high, not very low, some of them have a very, very high contribution, half an IQ point, so that's a lot towards the entire crowd, whereas some actually have negative contribution. For most of the crowds, it's actually better to leave them out. Yeah?
Are you using majority to estimate contribution?
So for this plot, we've used majority. We've actually tried to do the same thing using our machine learning aggregator. The results are not very different. They look almost the same. So yes, the aggregation method does have a slight impact on contextual IQ, but not very big. What really matters is your responses. Any other questions about this? Yeah.
So just to make sure I'm getting this right, this guy with the negative contextual IQ unlucky on this particular test, right? I mean, he has a good IQ.
Yeah, he has a mean IQ. What happens is whenever the crowd needs him the most, he turns to give the wrong answer. So I'm not sure whether to call it unlucky, but he's very similar to that crowd in terms of what he knows. And the places where the crowd actually fails, generally, he does even worse. Yeah.
I guess my question is this really something about this guy, or was he just unlucky on this particular day? Does it just, you know...
So it depends on the context, right? The context of this crowd.
If you order people, there will always be one on the top and one at the bottom. So I'm just
Yeah, but all these people have the same IQ score, right?
Right. But
I think the question is that this score is sort of group dependent, because if you consider a group where only this guy is the only soldier.
Yes, so hence the name contextual, right? It really does depend on the context of crowd in which you're measuring.
So in that sense, he is unlucky that he's part of that particular group.
Yeah, so he's a bad fit. Okay, I would use the term he's a bad fit for that specific crowd.
I'm still wondering if you can really draw that conclusion. Are you saying if you would now take a new test, take the same group, you think there's a high likelihood the same guy would again come out at the...
Yeah, so that's what we haven't tried, but that's my guess. That if we were to take, there's another version of Raven, the Raven test, for example, and it has the questions are very, very similar in nature, but different. My guess is that this guy would still have a low contextual IQ. Right? I'm sure there would be a difference, but I think I think there really is a fit within a crowd. He gets the same sort of stuff right. That's my guess, but we have never tested, so that's definitely worth testing. All right. So I just wanted to mention, our aggregation technique is just one of many aggregation techniques, right? I talked about machine learning-based aggregation. I talked about just majority voting. Obviously, there are other mechanisms for aggregating people's opinions. I guess one of the more famous one is prediction markets, where you let people actually place bets based on their prediction of future events. So there are several companies that make a nice business out of this. And there are lots of other aggregation mechanisms. The ones that we've used were very, very specific to our context, where you have multiple choice questions and only one answer is exactly correct, as opposed to this kind of a setting. So I want to talk a little bit more about the aggregation techniques themselves. Before I reach there, I wanted to discuss some famous crowdsourcing platforms and what changes a crowd's IQ in these platforms. So how many of you are familiar with Mechanical Turk? Raise your hands again. Okay, almost everybody. So this is one of the most prominent crowdsourcing platforms out there. It allows workers to get what's called in the Turk terminology hits, human intelligence tasks. These are basically pieces of work. They solve these works. And on the other side, you have people that publish these hits in order to have them solved by the crowd. So a very, very similar setting on these platforms. So we wanted to measure the IQ of a crowdsourcing platform like Amazon Mechanical Turk. Now, obviously, this is a very ill-defined question. What's the intelligence of Mechanical Turk, right? As if you can answer, okay, it's exactly 150 IQ points. But let's make this a bit more precise. There are a lot of things that impact the intelligence or the performance that you get on any task in such a crowdsourcing platform. One thing is the incentive that you offer. How much money are you offering? What are the conditions to get this money? When you consider someone to have solved a hit. Your choice of workers obviously affects the performance that you're going to get. If you only select very, very talented individuals or high reputation individuals, you're likely to get good results. The way you phrase your task also has an impact on performance. Of course, aggregation still plays a key role in the performance that you're going to get. And the interaction between the crowd members also affects your score. So let's be a bit more precise about how to quantify the impact of each of these on the performance that you're likely to get in crowdsourcing tasks. So one big question is whether you threaten to reject a hit in Mechanical Turk. So rejecting a hit means that you look at someone's solution to a task and you say, this is unacceptable. This guy deserves to get no payment, and I also want this to reflect on their reputation. So for every worker in Amazon Mechanical Turk, you have the rate of all hits that this guy has solved that were rejected. So a high rejection rate means that a lot of people disproved of the performance of this individual on many, many tasks in the past. So you probably don't want to use that individual. On the other hand, if someone has a sparkling clean reputation, that means he's probably done well, especially if he's done a lot of tasks. So one thing you can do is just in the phrasing of your task say, I will reject your hit unless you actually solve my question correctly. So basically that means take a look at the IQ question that I am about to present to you. If you're not sure that you know the right solution, you'd better not answer, because if you answer it incorrectly, you will not get any money for your solution, and this will reflect on your reputation. Well, guess what? This has a huge impact on performance. So again, by fixing a specific reward, so 10 cents per hit per question in our case, and fixing a crowd size, say 10 individuals, if you do not threaten to reject the hit, there are a lot of free riders, people that just try and solve the task because it won't reflect badly on them and they will still get their reward. So you have still quite a high IQ, 100, almost 120. But if you do threaten to reject the hits, then the IQ jumps through the roof. It's going to 140. So again, I don't think that is very surprising because people know when they know the answer to a question or not. If you threaten to reject their hits, they're not likely to take that answer. So there is a self-selection going on there. By doing this, you're essentially targeting only the individuals that are well suited to solving your task. So you would say, okay, well, I'll always threaten to reject someone's solution if it's incorrect. Well, one problem is you don't always know what the right solution is. That may be the reason why you're crowdsourcing this task to figure out what the right answer is. And beyond that, it has an impact on how many people actually try and solve your task. So you can also measure how many IQ points you get per minute in terms of the solutions. And as you can see, you have quite a high rate of answers and a high rate of IQ points that you get if you do not threaten to reject it. Whereas if you do threaten to reject it, then the rate of IQ, the rate of answers and the rate of IQ into your system drops by quite a lot. So if you need a fast solution to a question, you'd better be careful with threatening to reject people's hits.
But this is sort of related to what is your target level for the IQ, because we saw that with no rejections and with a crowd IQ of 20, it's just saturated. You'll never get to 130, 150.
Yes, that is absolutely true. But there is certainly a trade-off going on by how quickly you solve the task and the quality of what you get. Another thing that we tested is whether it's always better to pay people more for solving the task. Now, intuition might have it that if you offer a higher payment for the task, you'd attract more individuals and the quality that you get should be higher. So that's not entirely true. So it is true that if you increase the reward from 1 cent to 5 cents per question, then there is a big boost in IQ score as we measure it using this notion of crowd IQ. However, if you increase it further to 10 cents per question, IQ suddenly drops. One possible explanation for this is free riding. If you have a low reward for a task, then only people that are genuinely interested in solving this IQ test and find this interesting would solve the task. If you start offering 10 cents and even 20 cents per question, these are quite attractive for people that are just trying to free ride the system. To just try and guess an answer uniformly at random from all your answers to get the money. And that's the only thing they care about. And that actually decreases your performance. So paying more doesn't always help you get better results. You have to choose the right level in order to get your results. Yeah?
So this is with rejection or no rejection?
This is with rejection, I think. No, sorry. This is without rejection. Apologies.
Okay.
Without rejection.
What happens with rejection?
So that's another interesting question. My guess is you would still have this impact, because some people would try and free ride the system even with rejection, because they don't care much about their reputation, they have a false identity, and so on. But it might intimidate some people. So I think you would have the same effect, just lowered. Yeah.
You look at variability in the number of correct answers for the subject.
Well, we only had the subject participating once, so or you mean if he solves many questions?
Right. Because you would expect that, for example, you have a 0.1. Some subjects are still conscientious and are still trying to answer the right thing. But then a lot of these free riders are just getting almost all the answers wrong.
Yeah, so I would actually expect that to be the case. It's a bit hard to try and test that on the settings like Amazon Mechanical Turk, because what you do is each task stands on its own. You can't say, I want this specific individual to resolve a question. But that would be a very interesting thing to try and test. Yeah. Wow. Okay. Yes?
How do you know the left side that it's selection and not that they just try harder and put more effort
It could be that they put in more effort, right? It's just, so this is the data, the rest is my interpretation.
And one way you could distinguish it is by letting having no rejection and then changing it midway through and then seeing how many of them drop off.
In a controlled experiment setting, yes. That's something you could certainly do. I think this is easier to do, again, in a lab setting as opposed to Amazon Mechanical Turk. But certainly something that's worth considering. All right. A few more things about crowdsourcing environment. So again, I talked about a worker's reputation. And not surprisingly, the higher, one thing you can do in Mechanical Turk is select workers based on their reputations. You can say, I only accept responses from people with a reputation above, say, 98%. That 98% of their tasks were not rejected, and so on. So obviously, this has a huge impact on IQ, on crowd IQ. If you only select high reputation workers, your crowd IQ is quite high, 125. If you choose workers with a reputation level of, at most 80, then this crowd IQ drops to 90, even below the population mean. So this rewriting is really a big problem in these kind of settings. Yet another thing we've tried is to use our budget in a dynamic way. So what I mean by that is, rather than determining in advance that for every specific question in the task, you will take the opinions of, say, 10 individuals, you start by taking, say, 3 opinions of different individuals. On some questions, you will have reached consensus by then. So say all 3 people answered the same way. Whereas for other questions, you do not have consensus. And then you focus only on these questions where there is disagreement, where you actually need more data. So what this plot shows is that using a dynamic approach, you have a higher crowd IQ scores than by using just a static approach. So adaptively choosing where to seek more information certainly increases the performance. Okay, so to start concluding the talk, I want to focus on the classical crowdsourcing setting, which is you want to do 2 things. You have a question, maybe a multiple choice question, to which you don't know the answer. For example, the best label to describe an image, or just the best answer to a question that you have. You don't know the correct answers, and also you don't know who the best workers are. So suppose in this kind of a setting you wanted to select the best workers and hire them in future tasks. Well, that's kind of problematic, right? If you don't know what the correct responses are, you don't know how to figure out, even if you have the responses of the participants, you don't know which one of them were correct in a question and which weren't. So it's hard to find the best workers. So this is sort of like grading a test without knowing the answers, right? You have the responses that everyone has given you. You need to assign grades. You need to assign IQ scores to the individuals. But you don't know what the right answers are. So actually, people have looked at very, very similar settings like this in the past in something called item response theory from psychology. So our previous model, even our machine learning model, ignored the fact that different questions have different difficulty levels. Some questions are very, very easy. Some questions are very hard. Yet all I said is, an aptitude of an individual is their probability of solving any question correctly. In psychology, item response theory tries and models this. So essentially what happens there is there is a probability of answering a question correctly, and this depends on 2 things. First of all, it depends on the participant's skill. They call it the participant parameter, or the IQ. And it depends on the item parameter, the difficulty of the question. So what they do is they use a logistic function that translates the 2. So what you have here on the x-axis is the difference between the skill of an individual and the difficulty of the question. The difference between these 2 parameters. If there is a high difference, if the individual is much higher than the difficulty of the question, then he has a high probability of answering it correctly. Whereas if the question is much more difficult than the individual's level, then he has a very, very low probability of answering that question. So we've designed a machine learning model that we call DARE that relies on very, very similar things. So again, it's a probabilistic graphical model, and it jointly tries to estimate both the abilities of the participants and the difficulties of the questions. In this model, every question has a certain difficulty level, and every participant has an aptitude level. So the difficulty of a question is DQ, and the ability of a participant is AP. The participant's performance on a specific question is just their aptitude, their ability, plus some random noise. In this case, we've chosen Gaussian noise. if P's performance on a specific question is higher than the difficulty of the questions, then she knows the right answer for that specific question. And now the response depends on whether they know the answer or not. If they know the right answer, then they just choose the right answer. If they don't know the right answer, like in the previous model, they just take a guess uniformly at random. So again, using the same machine learning algorithm, we can estimate all these parameters simultaneously. So what I wanted to show is that, first of all, this allows you to estimate participants' abilities to quite a good level. So what we have on the x-axis here is the actual row IQ score, the actual number of correct responses that the participant had when we know the actual correct answers. And what we have here is the model row IQ score. So we let the model interpret and figure out what the right answer for each question is likely to be. And then we score using this set of correct answers. So the model infers what the correct answers are, and then we score participants based on what the model inferred. So as you can see, there is a very, very strong correlation between the actual IQ score and the model IQ score. So we do quite well in using this model in figuring out who the smart people are and what the correct answers are. Yes, Pushmit?
So if you know the right, the most intelligent person now, so the machine learning approach should perform as best as the best person.
Well, I don't know exactly, right? There is some error, right? Not all the points are on this diagonal line here, right? So if we knew exactly if our model was completely perfect, then all the points should be on this diagonal line here, where x equals y. Another interesting thing is that there are more mistakes towards this direction. So we tend to give people higher scores than they actually have. And there is a pretty straightforward explanation for this. Given the data, for some questions, we may select the wrong answer as the correct answer. Now, the answer that we are likely to have chosen, even using this model, is the one favored by the majority of participants. Right? So we make mistakes, and then we tend to believe something is wrong because a lot of people said so, and then we score them based on this answer, and all these people get it as if they had the correct response. Yes?
So in your experiments, do you always force them to give an answer, or can they skip?
Okay, so we don't, this relates to the actual data from the British standardization effort. So there they don't force people to answer a question, but there's no harm in doing so. So you just tell them that their score in this test is going to be the number of correct answers they have. They will not be punished for incorrect answers. So they're going to, if they think about it for a second, they'll probably take a guess, right? It can't hurt them. Yeah?
But these tests are often, as you said before, they are detractors, right?
Some of them, yes.
Like questions that, answers that, so I mean, the model can actually see it, right? So if you see, for example, in one answer that, they always either chose A or C, but never B or D.
Yeah, so the model isn't perfect. In some cases, right, you see that a lot of very, very smart individuals, up until the current question, tend to choose one answer. And there are a lot of people who have missed quite a few questions so far, and they tend to choose the other answer. So you'd say, okay, this looks as if there is a distractor. We haven't modeled specifically distractors here, but the model can actually interpret some of the data like this. Yes?
You try to model the variance in the answers. If a question is really hard, then you would expect people to have a variance.
Yes, so I didn't want to talk about this, but certainly we have a parameter here, this one, this gamma prior here, that we call discrimination. So some questions there is a clear cut, right? Unless you're above that specific skill level, no chance in hell that you're going to answer correctly, whereas other questions are more fuzzy. So that parameter basically dictates the amount of random noise that we add to the answer. So that's all I want to say about this for now. If you want to talk about this later, sure. Yeah. Yes?
But then do you think if you would penalize people for wrong answers and allow them to abstain, that might improve the crowd intelligence because it would reduce the noise?
Yes, that's certainly one thing that could allow them to basically give you that information saying we're not sure, or just put in their confidence level. That's certainly something that's worth considering. So okay, I want to wrap up a little bit right now. So. Okay, in the interest of time, I just want to say two things to wrap up. So another thing we looked at is determining whether some gold set answers can help us figure out who the smart participants are. So in this model, we have some questions that we provide the participants to which we already know the answer. So these are really screening questions, and that allows us to get some insight as to which participant knows what they're doing and which of the participants are just randomly guessing. Using these gold answer sets, our estimates become much better. So what we have on the x-axis here is the number of questions where we revealed the model the correct answer. We know this is the correct answer. And what we have on the y-axis is the proportion of the other questions, the one to which we did not provide the response, where we got it right using our model. So adding a little bit of ground truth actually helps our model a lot to figure out the ability levels of the participants and the correct responses. The next thing I wanted to say is, again, we can use an adaptive scheme to make a better use of our budget. So assume that you're allowed to ask, say, 10 questions. Your participants only have time to answer 10 questions. You can ask the question, which questions should you ask? A static approach basically uses the same set of questions for all participants, and an adaptive approach is something that is used in settings like GMAT tests and so on, where you look at the answer to the previous question and then you decide which next question to give to a specific participant. So as you can see using these lines here, the error rapidly drops if you use an adaptive approach, whereas in a static approach you need quite a few more questions to have the same error in a participant's ability level. So an adaptive approach like the ones that people use in GMAT tests is very, very good for these kinds of settings. Okay, so I want to just wrap up with a few takeaways from this talk. So first of all, aggregation certainly has the ability to improve decisions, but there are a few limitations to that. First of all, there are diminishing returns. Right? It's not as if you can aggregate 1 million individuals and expect a super genius IQ. The returns diminish. Another thing is crowds can outperform even their best members. Sometimes, for some settings, it's actually better to use everybody's opinions as opposed to just figuring out who the smartest guy is and only relying on their opinions. But this only works if the crowds are homogeneous enough. If there is a high heterogeneity, a lot of variance in people's abilities, you want to find out that specific individual. You can use machine learning to boost IQ points, but proper modeling is essential. If you don't put in the right kind of model, you can end up with a lot of noise. You can certainly quickly screen workers using gold answers, ground sets, and you can use adaptive approaches to do this with a lower budget. But these techniques are essential if you want to have good performance. One issue that I have not discussed through this talk is the incentive structures, except a little bit regarding mechanical Turk. There are a lot of crowdsourcing contest-based mechanisms to make sure the incentives are well suited for these kind of tasks. If you want to hear more about this, just grab me a bit later. So thank you very much.